in this Orion Uncover meeting. It's my great pleasure to introduce the last session of the part 1 of our meeting. We heard amazing talks already. They are all in our website. So if you want to replay them or hear them again, so go to the website and then click on the YouTube links. And if you want to contribute now to this new and last session, do it live on our YouTube chat. And on top of this, if you want to continue with even more discussions after these talks, you can also use our Google Groups. So we are starting today this last session with Bob Odell. Hello, Bob. Can you hear us?
Yes, indeed.
Great. So let me your talk here. Yeah. So Bob is speaking from Vanderbilt University, and he will talk about the third star formation region and layers in the Orion Nebula. So when you want, everything is ready for your presentation.
Fine. I have taken the liberty of adding additional subject to my talk, things that have developed since submitting my abstract. Let me show my collaborators. They include Neke Bell in the red shirt, Gary Furlan. Baby Trump played no role in the work you are about to hear. Of course, we're familiar with the inner part of the Orion Nebula, the so-called Huygens region. It's an even more interesting view if you take pictures made over a 20-year basis with the Hubble Space Telescope and take a ratio of them. And what you see is that there are many motions here, 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 here that originate from this region. This region includes a circle for the H1 boundary of absorption in the Orion South molecular cloud. This line is the ionization front facing Theta 1 Orion SC. So those are based on pictures. This shows how it looks in velocity space. This is from it's an 03 velocity coded image made by Takao Doi, a graduate student of mine some 20 years ago at this point. Interesting student. He did it, his PhD, in between flights as a shuttle astronaut with the Japanese Space Agency. So this Orion South cloud is basically free floating. You see here in the illustration, the observers at the top, Theta 1c is here, the main ionization front, and we see in the radial continuum formaldehyde and H1 in absorption, which means that the nebula is ionized behind it. So that either puts it here at the closest or this high, because if it was any closer to the observer, we would not see the characteristic boundary, ionization boundary. Now, when we see a picture of Orion, we're seeing it as if it were painted on the sky. But if you take velocity information, you see that it's actually multiple layers. The closest to it, the velocities I give here are all relative to the Orion molecular cloud. Veil A, Veil B were discovered by Van der Werf and Goff some 30 years ago. Ignore the O1 layer in this paper. Then there is an additional layer of material crossing the entire Huygens region. Then a cavity around theta 1c. Now, there is an additional feature that shows up on even color images like this. It's labeled a high ionization arc. Shows up even better if you have a ratio image of low ionization nitrogen 2 as compared with higher ionization oxygen 3. And you see that there is an arc of high ionization that is dark in this case, that almost circles theta 1c. It's interrupted by the Orion South molecular cloud. Now, we showed in a paper some 10 years ago that inside of this a circle, it's a cavity. There's little material surrounding theta 1c, and I can't go into the reasons there, but it's one of those few clear-cut papers I have ever read. So there is an inner wind-blown cavity there. Now, that presents a certain problem in the discussion of what's the nature of veil B, where it is argued, argued earlier in this paper by Cornelia Pops, that this was a wind-blown bubble out here. Problem with that interpretation is there are other layers in between, both this layer and this layer, and this is clearly a wind-blown cavity here. So that I think we need, any interpretation of this needs to factor in that there are multiple layers inside it that would directly interfere with the stellar wind, at least at the present. Now notice that all of these velocities with respect to the molecular cloud are blue shifted, and the velocities decrease in the amount of blue shift as you go outward. This tells you immediately these are not the results of a single event, with the fastest moving things being farther out. How do we know they're farther out? Because some layers we see certain ions. And indeed, in a paper just published by Nick A. Bell, that we were able to determine the distances for each of these layers. This was done by comparing the predictions of photoionization models with the observations, and in particular, the outer bubble layer here, we concluded is at 2 parsecs, 2.0 parsecs displacement with respect to theta 1c. That layer has not only the forbidden carbon 2 that Cornelia was talking about, but also has molecular hydrogen and H1 in it. So there are these various things that are there in it allow you to determine its distance. We don't have to draw on geometry. Likewise, when you look at this inner ionization layer, it is fairly close to the trapezium as compared with the outer bubble. And of course, here we have the nearer shell of gas that's expanding from the cavity in the middle. So it's a complex region, and it's important to understand what is where, because this Orion South molecular cloud is basically floating in the middle of it, and suspended is a certain term you can use, and lots of stellar outflows there. And important thing is that they are visible. The outflows, sometimes in both directions, are visible. It means these stars are sorry about that. It's that these stars are just beneath the ionized surface. This is unlike the Orion cluster. It's unlike BNKL. And the other carry away from this is that there are multiple layers in the Huygens region. We need to look at all of the developed data that's available in order to decipher what is going on. Now, let me just flash up some references here so that they appear in the record of the proceedings here. Other listeners who are interested are invited to look at those, because I've tried to highlight the most important papers with respect to what I've been discussing. And that's it. 10 minutes, 30 seconds.
Thank you very much. So I think that there were so many questions that people start calling you to see if they can directly ask you on the spot.
I wish it were that.
Yeah. So we have a question from from Jan Fabrich. Let me read this to you.
Yes.
So the question is, what techniques can we use to determine the distances between these layers?
What is the method I used?
No, which techniques can we use to determine the relative distances between them and to improve our knowledge about these distances?
Well, the only one I know of is the one we use, which is looking at the spectra of each of these layers, both in absorption lines and emission lines, and do photoionization modeling based on to determine the distance and density and distance conditions that will explain them.
Mm-hmm. Really good. So while we wait for some questions here, I have one myself, because you are showing this Orion South cloud, which I think, if I remember well, is also forming a lot of stars inside, and you were showing also the outflows in the past. Is this region well shielded? So is living in this super extreme environment, but is it well shielded inside, or the radiation is still affecting what is happening inside this?
What word did you say after well? Is it well suited or?
No, well shielded. So is the gas inside this Orion South region still cold and molecular, or is irradiated so much inside?
It is cold and cold, because we do see formaldehyde and absorption in its spectrum against the radial continuum formed by the main ionization front. And also you see it in H1 in absorption. Years ago with Will Henney, we did actual models to explain those conditions. So that's the importance of this line, which marks the ionized surface of the molecular cloud. That, of course, faces theta 1c, because the cloud is much bigger. This is just its densest core. It's less dense out here, and then only at the surface is it photoionized.
Oh, really good.
Most of the young stars in the area are in here. They're not down in the core, even the X-ray sources. So most of the new stars, the sources of those outflows are right in this region. Like you see here.
Mm-hmm. Really good. Yeah, as I also want to remind our audience that Bob gave one of the really interesting talks in the previous Orion meeting. So everything is recorded, and he was talking actually, if I remember well, about the outflows and all the outflow structure in this Orion Nebula cluster. So thank you very much for contributing again, Bob. We give you a big round of applause here. Good, and we move on to our next speaker. So John Tobin, let me bring you up here. So hello, John.
Hello.
Hello, we hear you well. So John is from NREO in the USA, and he will talk about, let me bring your screen here. He will talk about his new VLA ALMA Nascent disk and multiplicity survey in the Orion molecular cloud. So everything works well, and you can start whenever you want, John.
Okay, thank you very much. I'm glad to be giving an online talk at this conference again. And so we've been using ALMA to conduct the VLA Nascent Disk and Multiplicity Survey of Orion this time. And this project would be possible without the help of my collaborators. I want to specifically point out the contributions that Patrick Sheehan has made to this project. And then all of the collaborators that are highlighted in yellow here are students that have participated at some stage of their career on this survey. Okay, first, why study protostellar disks? So protostellar disks are the younger disks that are still embedded with an infalling cloud of gas and dust, and the disks around protostars are still relatively unknown. And we don't know if these disks are likely to be unstable. Their properties might depend on the physics of collapse. And no matter what, they're the initial conditions for disk evolution and possibly planet formation. And so in these images that I've adapted from Crater et al. 2010, I just show maybe the variety of disks that we could possibly see towards protostars. You might see a very small disk that doesn't have a lot of structure, not very unstable, to larger disks without instabilities, and then towards even larger, more massive disks with instabilities, possibly leading to companion star formation. And so the VANDAM survey, we've done the VANDAM survey of Perseus, which I won't talk about here, but I'm going to talk about the VANDAM survey of Orion, which is the second survey, which was done with the VLA and ALMA. ALMA observed 328 protostars in Orion, and then we also observed 150 of these with the VLA. And a resolution was on average about 30 to 40 AU, so about 0.1 arc seconds at 870 micron and 9 millimeter with the VLA. This is a spatial distribution of our sources in the Orion molecular cloud. So we cover all of the known protostars that were identified by Spitzer and Herschel in the Orion A and Orion B molecular clouds. Everything marked with a cross on here was observed with ALMA, and all of the ones that are blue points are the class 0 protostars, and those were all observed with the VLA as well. So we cover the full range of environments within the Orion star-forming cloud, except the innermost part near the nebula. And so now just to give you a taste of the sources that we see, these are the ALMA observations toward a random assortment of the protostars in the sample. So I think this is fairly representative. You see some of these are small structures, some are large structures, and I removed the binaries from this purposefully, but there is one binary, or actually this is a triple that you can see here. And then when we shift to the VLA wavelength, you get a bit of a different view. So now for the one multiple that I included in this plot, you can see the second source budding off of the brightest source here. But the structure of the disks appears to change depending on wavelength. So you see when you move to the VLA wavelengths, longer wavelengths, everything appears a bit more compact. We're still analyzing this and trying to determine, is this a reflection of dust evolution, or is this just the surface brightness sensitivity of the instrument with the VLA being different from ALMA? And so we're still analyzing that, but we have a very large sample so going on. These are still some more class zeros observed with ALMA. These are class 1 and flat spectrum sources observed with ALMA. So we see a wide variety of structure towards these protostellar disks. And so now we finally have a large sample that enables a true examination of the disk demographics. So we're no longer really concerned with the debate about whether or not there is a disk. I think the pictures speak for themselves. And now we can move toward looking at what's the distribution of radii and masses, and can we determine if these properties, the radii and masses, depend on anything? And we also detect a large sample of multiple systems, but that is another talk in and of itself. So I'll concentrate on the disks here. So first, starting on the disk radii. So on the y-axis, I am plotting the disk radius as measured from two-dimensional Gaussian fitting. And on the x-axis is bolometric temperature plotted backwards. So the class zeros are here, class ones are here. And you can see there's really no clear evolution, or there's no systematic evolution of disk radius with the evolution of the protostar. The class zeros tend to be a bit larger. I put the median radii in the upper left, a bit larger than the class 1 and flat spectrum, but from these distributions, they don't look like they're all that different. And now if I put this in a cumulative distribution just to try and highlight the differences a little bit better, you can see that the class zeros are systematically larger than the class 1 and flat spectrum disks, but not by a lot. And the single line that I plot here, this is the distribution of disk radii from Matthew Bates' 2018 study of disks observed in his simulation. So his simulations are finding disks that are systematically larger than what we are measuring. But what we can say is that while very large disks greater than 100 AU are not the most common disks, about 25% of class 0 disks are larger than 50 AU. So class 0 disks that are bigger than 50 AU are not uncommon. Now, comparing these to the Proto-Planetary disk samples, so now the Orion disks are plotted as these solid lines, and the Proto-Planetary disks in different regions labeled are the shaded regions. And so the Orion disks tend to be smaller than Taurus and Lupus, but they then tend to be bigger than some of the other disks in Chameleon and Upper SCO and AONC. So we don't quite know what to make of that, but it seems that there's not a systematic evolution of disk sizes going from class 0 to class 2 sources. And so why are the disk radii small compared to some protoplanetary disks? We're not exactly sure. It could be a myriad of things. It could be viscous spreading of those more evolved disks. It could also be radial drift of the large dust grains is making the disks appear small. Or maybe these protostars are creating constant angular momentum with time, such that the disk isn't growing very large. Or maybe there's MHD disk winds that are removing angular momentum from the system without actually growing the disk. And so this will need further study. Now moving on to the disk masses versus bolometric temperature. So disk masses on the y-axis, bolometric temperature is on the x. And again, there is a huge spread in masses. The downward-facing triangles are the upper limits, but the scatters over 2 orders of magnitude. The median masses for class zeros tend to be larger than class 1 and flat spectrum disks. So the class zeros tend to be more massive, but not significantly more massive. And then again, there's no clear systematic trend of decreasing disk mass with evolution. Now, if I plot these as a cumulative distribution, and now I'm showing the masses and Earth masses, you can see the separation of the class 0 and class 1 and flat spectrum sources. And I'll note that the distributions of class 1 and flat spectrum are statistically indistinguishable from each other. And now comparing these to some other protostars, these are the disks that were observed in Perseus by Lucas Kogonitz in 2018. Perseus was systematically more massive. And then if I compare it to the study by Jonathan Williams and Ophiuchus, the Orion disks are systematically more massive than the disks in Ophiuchus by a large margin. So what is going on here? Sorry, I forgot. I overlaid the Taurus disks from Sheehan et al., which are in agreement with the Orion disks despite different methods. And so what's going on with these Perseus disks? Perseus was from 9 millimeter flux densities that were corrected for free emission. This might have some systematics associated with it. And I think an ALMA survey or a compilation of the archival observations is going to be needed to see if there is really a difference. And for the Ophiuchus sources, Ophiuchus is known to have significant extinction, and so it's possible that an extincted class 2 population is contaminating the protostar sample. But as you can see, this still isn't going to fully resolve the inconsistency, even if we had some contamination from older sources. So I think we have a bit of a mystery, and maybe there shouldn't be an expectation that disks evolve the same from one region to the next. And now compared to the protoplanetary disk samples, Orion is significantly more massive than the observed protoplanetary disk samples by about a factor of 10. And so if you want to form giant planets, you need about a core about 10 Earth masses. And so most of these protoplanetary disks do not have the mass required to make a single core of a giant planet. So if we want to understand giant planet formation, we might need to look at these protostellar disks. And so I think it's reasonably clear that we should expect some evolution towards a decrease in disk mass, but whether or not that is going to be the same for all regions is still unclear. There's been some other studies that are showing that some disks are systematically less massive than other regions, even at similar ages. But the other thing we need to understand is this really an evolution of mass, or are we looking at conversion from small dust grains to larger dust grains that aren't emitting efficiently?
You have 1 minute, John.
Okay, I'm coming to the end. And so I think one of the great things about Orion is that we have all of these phases of star formation in one place, and we're beginning to look in just one region where we have a complete sample of everything, and that's in OMC2. And so Circa Van Terwiska yesterday showed you the distribution of disk masses in OMC2, and we can compare to that same region from our survey, and we see this clear evolution from class 0 to class 1 to flat spectrum, where actually a lot of the protostars are sort of mixed together, but the class 2s are clearly at the bottom of this distribution. So Orion's the place to be to study the full range of disk evolution. And just to highlight that we might be seeing indications of planet formation, these are disks with substructure that we detected in our survey of Orion towards what are thought to be protostars, but these look a lot like transition disks. And we're obtaining follow-up of these at the moment to try to characterize them better. And so on what does disk mass depend? It's not exactly clear at the moment, and I'm going to skip over I'm going to go quickly. I'm not going to read all this, but the assumptions we make in measuring disk masses are important, and I glossed over a lot of details, but radiative transfer modeling is being conducted for about 100 sources led by Patrick Sheehan. And this is just up here for the record, just to show you the median disk sizes, maximum sizes, the median masses, and the median masses of the sample for the total sample and the sample excluding multiple systems. So this is my summary. So I hope I've convinced you that we're detecting a lot of disks that are about 50 AU towards class 0 protostars, and we've now in Orion characterized this entire sample of disks. And disk radii are roughly constant with evolution. Disk masses are systematically declining, but very, very slightly, and there's a lot of scatter. And the young disks are significantly more massive than the more evolved protoplanetary disks. But I think what this leads us to is that we really need radiative transfer modeling to better understand this. Thank you very much.
Yeah, thank you, John. Really good. Yeah, so while we wait for more questions from the audience and the YouTube, I have a question for you because you were showing this comparison with, I think it was Matthew Bates' simulations without binaries, if I understood correctly. So is this a sign, what you find that is off, is this a sign of a binary truncation of the disks or some interactions with companions or something similar?
Yes, so I don't know that I'm only comparing the non-multiple systems for the sake of brevity in this talk, but also if I looked at the entire sample, there was still a systematic shift in the distribution towards larger radii in the simulation. So I think the simulations are measuring larger disk radii than what we measure in the observations. There are obviously some limitations to any simulation, so maybe it has to go with the initial conditions and the physics that were included. But I think some more analysis of that will be necessary.
Really good. So are there more questions here from the audience? Okay, so if not, I will quote you as, to say goodbye. Say the Orion is the place to go, and not only for this, but for many other things. So thank you for contributing. Thank you, John.
All right. Thanks, John.
Good. So our next speaker is Wangi Lim, if I pronounce this correctly.
Hello.
Hello. Hello. Now I see your screen.
Okay.
Yeah,
So can
here.
you see my slide also?
Yes, I see the slide. So Wangi Lim will talk about star cluster formation in Orion A. So everything works. It's all yours.
Okay, thank you. Okay, I am Wangi Lim, a postdoctoral fellow at Sophia Science Center. So this is a talk which I introduced to you about new analysis method to trace the observational evidence or any fossils of the cloud-cloud collision in Orion A and their effect onto star cluster formation. So the right figure basically shows the Orion A structure by the 13CO zeros momentum map by the John Belly in 1987, and then we see clear filamentary structure, dense structures there, and then later people try to find the YSOs around, and then try to find the other association between YSO and the gas, and then this is basically onto that flow. So then so I can take the advantage as almost the other last talk of this conference, because I do not really need to explain about why we are working on the Orion A and what is the star formation, why it is important. The only remaining thing is cloud-cloud collision, which I need to actually explain to you. So cloud-cloud collision, as you see at the other bottom figures by the other Tasker and 2009, are actually happening onto the other rotating galaxy disks. And then they basically have really short colliding time scale. So that basically has a 1/5 of the orbital time. And they are actually possible major source of the GMC turbulence. And then they are also helping to subfragment the GMCs. And then therefore that they are actually possible important mechanism for star cluster formation. And then previously the number of studies actually claim Orion A area may undergo the cloud-cloud collision, and then by Nakamura et al. 2012, and then Fukui et al. 2018. And So, like as I said before, see, there were a number of studies that tried to explain about the association between YSO and gas in Orion A area, and then this is one of the most recent studies on the flow, and then which is done by Nicola Dario et al. 2017, and then they used the Nantan 2-meter 13CO221 observation, and then comparing that to the YSO properties by the SDSS3 opposite data. And then this project is called as InSync project. And then they looked at almost like a 2,700 YSOs in entire Orion A filamentary structure. And then they found from the kinematic, the comparison between like YSO and also the gas, they found that the younger stars are more associated with the other dense structures as we expected. But the InSync data has the like a near infrared spectroscopy, but the Nantan 2-meter telescope basically shows about like 30 arc seconds of the other angular resolution. So then like they cannot really directly compare the pixel by pixel. So what if we have higher angular resolution 13CO observation, and then can you really like compare YSO properties to that pixel position of the other CO observation? Luckily, there is a the observation by Karma and NRO to do that, and then like you already saw this nice what is it, the data cubes by the other Sumi's talk earlier today, and then the size comparing like by comparing the size, like the Karma NRO observation is basically this size comparing to the other Dario et al.'s work, and then it basically resided there. And it basically covers our OMC3, 2, and then the OMC1, OMC4, ONC, and also S1641 North, and also NGC 1999. So, so like this observation basically achieved like angular resolution about like 5 arcseconds. And then one needs to note that the InSync data basically has the other 6 arcseconds as the other nearest separation in between the YSOs. So we can basically compare the YSO position toward the 1 pixel of the other Karma NRO observation. So we can basically compare the properties, 13CO properties of that pixel to that the corresponding YSO. So this is a the comparison in between those. So I put so both panels shows the 13CO Karma NRO zeroth momentum map, and so left panel shows the YSO locations and also their ages, and it basically shows the other bluer color points are actually showing the younger population, and then green, yellow, red are showing the older population. And as we can see from these maps, the younger populations are more associated with the other denser structures here. And then you may not be able to see really in detail, but like L1641 North and also the NGC 1999 also has the really young YSOs inside. Okay, so this is the first result. So then we compared the velocity difference in between YSO to the 13CO. So we got the radial velocity from the InSync data of the YSO, and then compare the velocity, the profile of the 13CO on that pixel position. So then like we just like subtract those two things. So here I show the V13CO minus V YSO on the other y-axis, and also the YS ages on the other the x-axis on the other the upper plot, and then the bottom one actually shows the other 13CO 13CO mass surface density, which I derived from the other Karma NRO data. And then we see some trends here, but it's not really clear what happens. So then we compared to one of the GMC collision simulation by Benjamin Wu et al. Like 2017 and previous works. And then they so we just like compared to the other 2 different scenarios. So one is the non-colliding GMCs, and on the other the top panel, and then like the cloud collision in the other downer the bottom panel. And then the velocity difference as well as the mass surface density trends basically shows a little bit favoring the cloud collision scenario for this our observation for the entire the Orion A area analysis. And then we also moved on to the other individual stellar clusters, and then we see that some of those clusters, for example, ONC and OMC1 and also OMC4, as well as probably L16 for your nodes, and those three regions are more likely following the cloud collision scenario. But like NGC 1999 basically shows basically like favoring the non-colliding GMCs. So we may be able to say, okay, so northern part of the Orion A area may underwent the cloud collision, but like not the southern part of the Orion A area. Okay, so luckily also we had really nice observation by Paus et al. And then as you see from her talk in that earlier today, and then we also compared these C+ data toward the this like a 13CO data, and then comparing their velocity properties, which basically like overlapped on just like a northern part of the Orion A, and like the reason we do that is in the previous studies, the Thomas Bispas et al. Actually claimed that if we use the position offset and also the velocity offset in between CO and C+, that would be a evidence of the cloud collision. And then we have this really nice two results by the other Karma NRO 13CO and also the C+ observation by Sophia. So we just compared that. And then, yeah, this is the other map we compared. And so this is, these panels are actually showing the integrated intensities inside each the circles. So 4 circles, big circles like OMC3, OMC2, ONC, and also OMC4 are showing the location and the size of the clusters we are looking at. And then H1, H2 are actually showing the test regions, which basically we wanted to see effect of the other expanding shells. So so these integrated intensities do not really show really clear trends of the other the cloud collision. But like when you actually looked at the individual pixels, like these, so like we just randomly selected the 9 pixels from the other number 1 to 9, and these are showing some evidence of the cloud collision when we comparing to this simulation. So NCC basically shows the other non-colliding, and then CC basically shows the other cloud collision, and CC9P shows the H1 view of the other cloud collision. So as you can see, cloud collision basically shows the other velocity offset, and the 13CO. Oh, sorry. Well, the red is actually the C+ line, and also blue. The black line is actually showing 13CO line. So here we can see probably like a panel 2, 4, 5, and probably 6 and 7 may shows the some trend they favoring the other cloud collision. So those are basically in these all area like OMC3 and ONC and OMC4, and not clear for the OMC2. But like the H1 and 2 are actually showing just following the expanding shell shocks basically. So these may support the cloud collision scenario in Orion A area as the one of the mechanisms of the star cluster formation. And then here is my summary, and then yeah, you can look at this, and then like I'm happy to take any questions. Thank you.
Thank you very much. So we have a couple of questions here. So let me show this question now. This question is from the online audience. Marina Konkel asks, so how big in terms of mass, size, and density of the clouds do you need to collide?
Oh, so that is really critical question. And then these simulations basically shows the GMCs in the size of the mass of those GMCs are almost like 10 to the 5th solar mass. and then colliding speeds are almost like 10 kilometers per second. So that's probably one of the ideal case of the other GMCs, which basically generate these kind of cloud-cloud collisions.
Yeah, and also I have a question, because you are comparing these models of cloud-cloud collision, and I guess it's some cloud that evolves only by gravity, so there's no collision at all. But how much, then you compare luminosities of tracers, and how much this depends on the feedback, for instance, that you can illuminate regions and then produce shifts in the peaks, and how good also you recover the velocity of the gas, which is a full distribution, and you put it in a single velocity.
So I knew this will come up, and like that is really like a critical question. So this was a really short presentation, so I could not really bring up the issues of our project, but that is basically one of the biggest issues in our project, because our simulation do not really have any stellar feedback. So, but like we know the Orion A area, we basically have like a bunch of the stellar feedbacks around. So we do not, I cannot really say anything about that, because we do not have the other simulation of research on those. But I bet like those guys, such a big stellar feedback would basically have so a big, I don't know, like well, they will just affect like a lot, like on this kind of analysis.
Good. So we have a couple more questions from the audience. So let me show this here. So Enrique Vázquez Emadeni, so he asks, what mechanism could possibly accelerate clouds so massive to such high velocities?
So yes, the original idea that as I understand, was basically from the rotating disks of our galaxy. But the problem is the Orion A area is Orion basically clouds are basically about like a 400 parsec below the galactic plane. So we do not really have a bunch of the other neighborhood around. So I am not quite sure. So like the purpose of this project is something we need to figure out if we can really rule out or not the cloud-cloud collision as one of the important mechanisms in Orion A for the other star cluster formation. But so for now, since we do not have the stellar feedback and other detailed analysis, so right now we can only say we see some observational evidence of the cloud-cloud collision, but the further physical properties would need to be studied more in later studies.
Okay, and the last question also from the audience. So Gilberto Gomez, he has, so the 13CO and C+ velocity offsets could be sign of accretion toward the filament. So how would the cloud-cloud signature would be different?
Oh, that's also a nice question. So let me show one of the previous figures. Okay, so if you see this cloud-cloud collision, the feature, you can basically see a signals of like two peaks here. So one from the other the 13CO, and also the one from the other the C+. And then we are assuming that we may be able to see similar peaks in between CO and C+ in some sense. Well, even though like those are actually merged into some regions, but like if we see kind of like really old star clusters which basically held the cloud-cloud collision long before, then we may not be really able to resolve that. So like we basically need young enough the clump or star clusters which basically had the cloud-cloud collision like 2 or 3 megayears ago. But like if we see star clusters like I don't know, 10 billion years like old, then we may not be able to just like distinguish those two things.
Sorry. Yeah. So I suggest that we continue our discussions in the Google groups because we have to move on to the next speaker. Sure. So thank you, Wangi, again.
Thank you.
Good. So our next speaker, we have here Helen Kirk. Hello, Helen.
Hello.
Nice to see you.
Great. Can you see my first slide?
Yeah, let me share your screen. Oh, no, sorry, no, I don't have your screen yet, sorry.
Yep, sorry. Try again. There we go.
And now it's coming here. Yeah, there it is.
Great.
Good. Yeah. So we see your slides. So dense cores under pressure in the Orion A and the Gould belt result from gas. So everything works. We hear you well. So you can start whenever you want.
Great. Thanks very much. And thanks for the opportunity to talk about these results. So I'm going to be talking about sort of the virial nature of dense cores in Orion, as well as some other nearby star-forming regions. So as everybody knows, protostars form out of dense cores. Perhaps not every dense core forms a protostar, but at least some of them do. And when you look at an individual core, it's a little complicated to figure out what's going to happen to it in the future. We know that there's going to be self-gravity, thermal pressure, turbulence, cloud pressure, magnetic fields, and probably other things I'm not mentioning as well. And it can be really difficult for a single case to figure out what's going to happen. So just as an example, that image on the right is showing you a snapshot of part of the Orion A molecular cloud. All the little white blobs in there are dense cores, and you can see they have really irregular geometries, and their larger scale environment is quite complicated. So it's really tricky business. So what we've been doing instead is attempting to get a rough idea of what's going on a population level, doing just a very basic virial analysis. And the idea is that it may not be perfect core by core, but you get a sense of globally what's going on, and especially if you run the same analysis using similar data sets on multiple clouds, you can get a real sense of how the clouds compare to each other. And I should just put out a caveat that for the analysis I'm going to be showing you, I'm ignoring magnetic fields because we didn't have uniform data across all of our cloud sample for that. But I think it's starting to come, and that's really exciting. Okay, so first thing is how do we identify the dense cores? We were using data from the JCMT Gould Belt survey. That survey basically looked at all nearby molecular clouds that they could at 850 microns and 450 microns. So basically looking at cold dust glowing. And it has really good sensitivity, fairly good completeness. So we're basically finding just about all of the cold dense cores now with this survey. And as a bit of a side plug, the GBS has made all of our best reduced maps publicly available. See my 2018 paper for a link to that data. And if you're interested in maps for any region, Orion or anywhere else, and have any questions, please get in touch with me offline. But moving on to Orion A, we wanted to identify the dense cores. And so a few years ago, I had an undergrad student working with me, James Lane, and he produced a core catalog. In fact, he used two different source finding algorithms. And you can see in this little blow up just how important it is. So this is one of the more boring looking parts of Orion A. And you can see even here, there's quite a wealth of structure, and it's quite difficult to decide how to split things up. So I think it's always important in cases like this to try more than one source identification algorithm, just to make sure that your final conclusions don't matter too much into how you broke up the emission. But anyway, for today's talk, I'll just talk about one of those results using GET sources, which is very popular with the Herschel crowd. And basically, he found about 900 dense cores across Orion A, and about 2/3 of them had reliable sizes. So those are the only ones we're going to be talking about today for a virial analysis, because we need a good size for doing our next steps. And we matched them all up with Tom McGath's Spitzer Protostar catalog, and most of them are starless. Okay, so we have sizes and masses from the Gould Belt survey, but now we need the rest of the information. And that's where the Green Bank Ammonia survey comes in. So GAS was a several hundred hour project observing ammonia across the densest parts of nearby Gould Belt clouds. And the really great thing about ammonia is that you can get temperature and kinematics simultaneously. And it's also very sensitive to cold dense gas, which is exactly the same material that belongs to our dense cores. So it's very complementary. And again, data is public from this survey, not everywhere yet, but the first 4 regions observed, the maps and their property maps. So things like the derived temperature, the derived line centroid, everything like that, those are all published. And our team is working on getting the rest out the door soon. Okay, so now we have size, mass, temperature, non-thermal line width. What do these cores look like? We did a very simple alpha analysis. Probably most of you are familiar with that. So we pretend that all the non-thermal line width kind of acts like a uniform thermal pressure, which is probably wrong, but it's a simple thing to do, and that's usually what people do. And so in this plot that I'm showing on the bottom, we've got mass along the x-axis and this alpha parameter along the y-axis. And things below 2 are the ones that we expect to be gravitationally bound and forming protostars in the future. And you can see there's not very many points in that part of the plot, which was kind of scary because we know Orion A is forming lots of stars. We should expect lots of bound things. So we scratched our heads and puzzled for a bit. And then we realized that, of course, Orion A is a very dense environment. So these cores are living in the middle of quite a lot of molecular cloud material, and they're probably getting squished quite a lot. And so we should really account for that cloud squeezing pressure when we try to figure out whether they're bound or not. And so lucky for us, Marco Lombardi had already published a very nice total column density map of Orion A, which we can use to try and estimate how much pressure there is on the dense cores, making some very simple geometrical assumptions. The one complication was that the map was actually too good for our use. As you can see on the right-hand side, the resolution is pretty good, and you're actually measuring some material and contribution from individual dense cores. And obviously, we don't want to count that when we're trying to figure out the ambient molecular cloud environment. So we use something called an ATRU algorithm just to pull out the large-scale component of the molecular gas and that, or the cloud material, which is shown in that figure on the right now. And we use that as a proxy for how much squeezing was going on for individual cores. So what happens when we put that in, showing this plot on the right is now in slightly different units. It's in energy density space. So the horizontal axis is showing you the total virial equation. So things that are to the right of 1 are going to be bound by the combination of self-pressure and self-gravity and this cloud pressure. And the y-axis is showing you the relative contributions of self-gravity and the cloud pressure. So things that are on the bottom half of the plot, most of the binding is happening from cloud pressure, and on the top half of the plot, it would be from self-gravity. What you can see is that, much to our relief, many more of the dense cores appear to be bound, but that it is this cloud pressure that is doing the majority of the bounding. Okay, so you might be wondering, how does Orion A compare to other nearby molecular clouds? Since I told you it's important for these simple proxies to compare populations and not just look at one. And so I had an undergrad student working with me, Ronan Kerr, and he basically ran exactly the same analysis. So again, Gould belt survey data for identifying the dense cores, and then using gas data for the kinematics and temperature, and ran exactly the same analysis. And so here I'm showing you on the left-hand side, here's this, again, simple alpha parameterization. And again, you can see that just looking at thermal and non-thermal motions versus self-gravity, very few of the dense cores appear to be bound, which again is strange. But when you add in the pressure term, the situation again changes and many more of the cores appear bound. So something interesting that Ronan did was we looked at not only the cloud pressure, but we also took into account another pressure term, which is basically considering that the ambient environment around the cores are quite turbulent as well, and that lower density material with more turbulent motions might also be contributing some pressure. And so he put them both into that plot on the bottom right. And what's particularly interesting is when we run this comparison of those two pressures, this cloud weight pressure and this turbulent environment pressure, and compare those across the regions. And what you can see in that table I just popped up in the middle of the slide is that in Orion A, the cloud weight pressure is by far the most important thing. It's about more than a factor of 10 more important than the turbulent pressure. Whereas for the other three regions, that's not the case. The two terms are much closer in magnitude, and often, in fact, the turbulent pressure is the stronger one of the two. So that's quite interesting. So what we're finding is that across quite a wide range of nearby star-forming environments, pressure seems to be really important to bind the cores. If we don't include the pressure, many of them look unbound, and that is not what we expect since we know they're forming a lot of stars. In Orion A, cloud weight pressure is the dominant source of this binding, and that's quite different from other nearby star-forming regions. So that's something we might want to think about. Why is Orion so different than these other regions? I'd like to point out that many virial analyses still don't put in a pressure term. I think our results are showing that that's important to do. And really, I think the power of the type of analysis we're doing is because of new large-scale survey data. So we finally have these large area maps taken the same way over many different molecular clouds, and we can finally do this really fair comparison over large areas to be fairly unbiased, which is showing some really interesting results. At the bottom, I've put up a whole bunch of references to various papers if you're interested in more details. One that I didn't talk about but is actually really interesting and important is the last one there on the list, Jared Cowan, a PhD student at University of Victoria. He's been working on the role of core identification and analysis schemes on how much that changes your virial results. And depending on what you do, it can actually change things more than you might like. So I think that's something we should all keep in mind as we go forward with whatever analysis we do. Okay, thanks very much.
So thank you very much, Helen. Good. So, oops, you can keep your screen here if you want. Yeah.
Great.
So there is a question from the audience. So Con, he asks, so does that contradict the hierarchical fragmentation because cores start with non-cell gravitating?
Yeah, that's an interesting question. I'm not really sure. I mean, it's certainly, I think our group is still really grappling with how non-self-gravitating the cores appear to be. And that has been quite unexpected. I'll have to think more about that. Maybe we'll follow up in the online chat. Good question. Thanks.
Yeah, great suggestion. Great suggestion. Indeed. So I have also a question because you are talking about turbulent pressure and about gravitational pressure from the cloud.
Mm-hmm.
But what about thermal pressure? Do you consider this, and perhaps because in regions like around the nebula cluster where you have all these hot gas that we have seen in previous talks, that will help you a bit in this case to pressurize your cores as well?
Ah, I see. So a binding term from the ambient thermal pressure. I think for the regions we've been looking at, that's probably not as big a factor as the turbulent pressure. I mean, it ended up not being a big term for most of. I mean, most of Orion is not so hot like that. There are little pockets of regions, but most of it not so much. And the other regions, I think, generally are fairly cool, at least based on the ammonia data. So I think the non-thermal line widths are probably would give a larger pressure term. But you're right, that would be something that would be interesting to look into for some regions, for sure.
Really good. So there is another question from Enrique Vázquez Amadeni. I will put it here. Actually, there are two questions, so you can answer one after the other. So the first question is, he said that perhaps he missed it, but how do you compute the cloud weight pressure?
Sure, I kind of glossed over that. So basically, we use column density, the local column density at the location of the core, and then the mean column density of the larger region as a proxy for how embedded the core is within the cloud to get a sense of the binding pressure. The equation is in the slides. It's basically a spherical symmetry approximation, and assuming that your local column is a proxy for how embedded you are within the larger structure relative to the mean column of the area. It's not perfect, but it seems to be okay and probably about the best we can do with the data we have.
Yeah, and the second part of Enrique's question, so can the turbulent pressure be run pressure due to accretion from the clouds?
I don't see why not. Again, we did a very simple, easy approximation based in part on what data we had uniformly available over our complete regions. If you were trying to attribute it specifically to accretion, I imagine you'd want to be a bit more careful about what line tracers you were using and think a bit more carefully. But certainly that could be done. That would be quite interesting to look at.
Yeah, I guess also it's really difficult to distinguish the two from observations, right? There is something that is pushing turbulently, if you want.
Yeah.
But what is the origin of this turbulence is perhaps really tough.
Yeah, I mean, if we had, I don't know, some like HC apply good infall tracers, that would be, you might be able to do a bit better. We were just using, I think, 13CO everywhere because that was what we had. So if you had large scale molecular maps and an infall tracer, sure, that would be a great thing to look at. More data.
Not really good. So we have
Sorry, go ahead.
no, we have an ongoing discussion in the chat that can continue later on in the group, which I think is great. So we thank you again, Helen. Thank you very much.
Great.
Good, and we move to our next and last speaker. Brian Mason, he's here with us. He has the honor of giving us the last online talk of the meeting. No pressure, no pressure. So yeah, let me look for your screen. Here it is. And if you can put your screen or your presentation in full.
Can you hear me?
I think so. It should be fine.
Okay. All right, thank you. I come at this from a little bit different of a perspective, which is that of an observational cosmologist and also working closely with instrument development. A lot of times we point our new instruments at Orion to make sure it's working right. This was a project I got involved in a few years ago that I've gotten really interested in. So I'm quite happy to be here and have the chance to talk with you guys who have all spent a lot of time thinking about Orion and all the interesting physics that it contains. I've just listed here some of my collaborators and highlighted the early career scientists who've contributed to this work. So I don't need to convince you guys that dust is important, but why do we want to look at it at long wavelengths? So we've heard from John Tobin before in this session and previously in this meeting that 3 millimeters is commonly used as a mass tracer for a variety of reasons. But of course, in order to do that, you need to derive those masses, you need to know the opacity, which depends on the grain physics. So we're used to thinking about the dust grain opacity being a simple power law, which a lot of times it is over quite a wide range of frequencies. But life need not be so simple. And then you go and make measurements way out here or even beyond, which is what I'll talk about today. So with all of that in mind, a few years ago, Scott Schnee had the idea for a project to use Mustang, which was at the time, new bolometer camera on the GBT operating at 3 millimeters to make a map of the dust emission in the integral shaped filament, OMC23. It's a very well studied object, especially in recent years, a lot of data have become available. There we had catalogs of starless cores, protostars, and young stars. And this is the map we obtained. It's but this is about 15 arc minutes. I guess you know that. This was published in 2014 in a paper by Scott Schnee. And the map has about a 9 arc second resolution. And I'll just mention this map was calibrated with respect to WMAP measurements of planet temperatures. So to put that in context, we had this Mambo map at 1 millimeter, which we used to infer beta. And we found, just to sort of cut to the chase and summarize the result of this paper, we found surprisingly ostensibly low values of beta. sort of typical values of 0.9 when you compare the 3 millimeter and the 1 millimeter data and assume a power law. I won't talk a lot about this right now, but we convinced ourselves, and I hope to convince you today, that this is not due to some weird systematic in the 3 millimeter data. Subsequent to that, Sarah Sadavoy put together a very nice paper that combined our data with Herschel data, observations of this object, with newly obtained Gizmo 2 millimeter data from the IRM 30 meter and Scuba 2 data to get really well sampled SEDs over the whole range from 160 microns out to our data point at 3 millimeters. And the result of that was kind of interesting. It indicated that, in fact, beta was close to sort of typical expected values if you consider the 2 millimeter and shorter data. And it was really just the 3 millimeter point that consistently lay above that model. And so if you take this, just illustrates, if you consider just the Mambo 1 millimeter data with our data, you get values sort of 0.9, but that's not indicative of what's going on over this whole region. So that was interesting. We were pretty confident in this result, but it was hard to explain. I will say I was quite relieved when we were able to get some public ALMA band 3 data and cross-check the fluxes, which agreed with our fluxes. But then subsequently, in the past, so about 2 years ago, we got a new bolometer camera on the GBT, Mustang 2, which is much more sensitive and much more capable than the original Mustang instrument that we were working with at the time. Of particular relevance, it has a much larger field of view, so that makes it easier to robustly map extended objects like the integral-shaped filament. So this was installed on the GBT in December of 2016. In late December, we collected our first data with it, and the integral-shaped filament was literally the first thing we pointed at, other than like 3C279. We took 1 hour of data, this is commissioning data, and made a map. The results of this and other work I'll talk about are on the archive and in the final stages of the refereeing process right now. We also got, based on what we saw, we got follow-up DDT observations with the GBT at 1 centimeter. So we have targeted photometry at a couple of dozen points on the integral-shaped filament at 1 centimeter. So this is our map. I like it a lot. We were pretty convinced when we looked at this that the telescope, that the instrument, the camera was working right. We thought maybe there was something wrong with our map making software at the edge of the map. Of course, we realized later it's M43. But I mentioned the field of view. So this map, like I said, it took 1 hour to make, and we made the map in the middle of the night. That's not this map, but essentially the map just fell out of the instrument and agreed beautifully with the previous result. We were able to cross-calibrate this with the ALMA flux scale, and these are just different ways of quantifying that agreement. So this map agrees quite well with our previous result, which again, we were happy to see. So we took this data, smoothed it down to the Herschel 350 micron resolution, and undertook a similar SED analysis, now adding in also our 1 centimeter observations from the GBT. And without going into too much detail, we basically selected 24 regions to focus on for the SED analysis, which are indicated by these slices here. That sample a variety of structures, the filament itself, starless cores, sources with known free emission from VLA observations, and extracted their SEDs, fitting out local variations in each map. And ended up with nicely sampled SEDs from 1 centimeter to 160 microns. These are some representative SEDs that we see. And again, we see very similar results as before with a sort of conventional single power law, beta 1.7-ish at 2 millimeters and shorter, but sort of a break in the spectrum at 3 millimeters that appears to continue out to 1 centimeter. Of course, we don't have any measurements in here, so we don't actually know the shape in there. And this, the point of this is basically almost all the individual SED points at 3 millimeter and 1 centimeter lie above the fit you get to a single power law if you just use the 2 millimeter and lower data and shorter wavelength data. So this is a breakdown by object type, and you see generally sensible trends, beta increasing in denser environments, temperature increasing. It is interesting that, we sort of fit this empirically with a double power law, with an independent power law for the data below 2 millimeters. And for the long wavelength data, we see effectively beta values of more like 0.7 or 0.8. And the break is most pronounced in the filament. Something funny is going on with the starless cores. I'm not sure what to say about that, but those are the spectra we see. So the interpretation, on average, the 3 millimeter point is about a factor of 1.8 above the fit that we get to the shorter wavelength data, assuming a single power law opacity. The 1 centimeter data is a factor of just over 5 above that. This is not a plausible calibration uncertainty. We've calibrated it 2 different ways and verified it with ALMA calibration. The GBT beam is very stable and well characterized, and we also measure it with out-of-focus holography several times each night and correct it the active surface. Spectral line contamination was something we worried about initially. The numbers don't really work out for that. We were also able to check that with public ALMA data, actually looking at the spectra. So I'm going to spend most of the rest of my time talking about a couple of possible contributors to this spectral signature we see at long wavelengths, in particular anomalous microwave emission or spinning dust. That doesn't, on the face of it, seem likely to explain all of what we see, or even the 3 millimeter data, because it typically peaks between 20 and 50 gigahertz, but I'll say a little more about that. And they're also theoretically well motivated, and I should say based on lab measurements, there are some models of dust grain emission which predict increased emissivity at long wavelengths, and I've just listed a couple of references there. So first, the spinning dust. This is from the very nice review by Clive Dickinson. So spinning dust, if you're, I think many of you are probably familiar, but it comes from a population, it's thought to come, sorry, the anomalous microwave emission is thought to come from a population of very small charged dust grains which are rotating just because of their temperature. And that gives rise to these spectra, whose detailed shape depends on the environment, depends on the radiation field, the density, and other parameters. And this is just a range of sort of canonical models that are used to represent what we expect spinning dust to look like in different environments. And this is the so-called molecular cloud model, and this is a dark cloud model. Oh boy. So so the shape of this is not sufficient to explain all of what we see. It could contribute to the 1 centimeter data, or perhaps with some exotic sort of exotic physics going on. It could contribute to the 3 millimeter data point, but it's not likely to explain both of them. And I will just say the models that are typically used are very simplistic, and we need better models. This is a very nice paper by Nathalie Guissard, which has used radiative transfer to actually calculate what you expect to see from spinning dust and molecular clouds properly. This is the emissivities from some of the amorphous silicate dust models I mentioned before, which I'll show in the next slide. Qualitatively agree with our data. We haven't done a careful quantitative comparison, but they do show the right trends in the relevant temperature regime. So this is just their 17 Kelvin dust model compared to the residuals from our data when it's fit to a single power law opacity at the short wavelengths. And again, so the amorphous dust can be fit, could explain our 3 millimeter point, but it doesn't do as well with the 1 centimeter point, and the converse is true for the AME models. We've got quite a bit of other data. Sarah Sadavoy has led the charge on that, so we're working on this. And we've also proposed to look at other objects in different environments with Mustang 2 on the GBT to answer to see if we see this in different environments, or if this is just a consequence of the very particular unique high densities and high strong radiation fields present in OMC2-3. So that's my conclusion, and I think I'll take questions.
Yeah, thank you very much. Yes, so we have a question from the audience directly, but I will read it to you. So let me go back here. So Jan Fabrice asked, so how do you deal with the beta T degeneracy in the SAD fitting?
So with the sampling we have, the parameters are quite well constrained. For the initial analysis of Schnee et al., we used ammonia data, and we did compare these results to ammonia, and they're generally in agreement, also from GAS.
We have a question from the audience. Yeah, so Amelia is here.
I was just curious about the spinning dust models, if the mechanism that underpins why the grains would be spinning is the same that causes a linear polarization. No.
So the anomalous microwave emission needs to come from very small grains in order for them to be spinning at the right rate to emit in the microwave regime. The small grains are not as well aligned as the large grains are responsible for the thermal dust emission. So just because they tumble in.
Really good. And I also have a question myself, because I mean you are covering already so many frequencies that it's hard to think about a frequency in between that can help you, right? Because all the results are clear. But so it would help you to do, and we mentioned this in one of the discussions, but combination with extinction and whether this will allow you to constrain a bit more the models, and whether we can learn how to combine these two data, for instance, in this meeting.
So I think the part of the SCD between 3 millimeters and sort of 20 gigahertz is the most crucial to probe to understand what we see here, what the shape of the spectrum is here. If it's really just a broken power law, which is just a purely empirical fit. If it's because of anomalous microwave emission, it should have some curvature and show a distinct peak at some frequency in that range.
Okay. So if there are no more questions neither from the online audience or here, so we thank Brian again. Yeah, and that finishes our part 1 of this amazing Orion conference. So we want to thank all the speakers again for these great talks in 2 days. And just to let you know that we will continue for another 3 days here in Leiden. We have already 15 topics to discuss in our unconference session. We will try to summarize them at the end a bit. We will put the slides, if we can, from all the speakers also online. And in the meantime, you can access to all the videos that we recorded in these days, as well as the previous videos that we had in the previous Orion sessions and the previous broadcasts. So from the organizing committee, we would like to thank you for watching us and following us all these days, being active in the audience, and stay tuned because we will repeat for sure this experience. Thank you again.